Let me say again, thanks for showing up, especially early in the morning, all 3 days, and on a Saturday to boot. Much obliged. So, let's see. Well, I don't know what to say now. So I think I'll say everything, at least everything that I can say in 1 hour. Topology is a big subject, and most people don't think of it as being applied yet, but times are changing and attitudes are changing too. So what I'm going to do for this lecture is just run through a whole bunch of ideas, future directions. If you find yourself interested in doing something that's a little bit out of the mainstream, then I hope I'll touch on something in this talk that might be an interesting open direction for you to think about. I'm going to go fast, and I'm not going to give all the details, and sometimes I'm just going to make up stuff as I go along. First, let me do propaganda. So topology is a big subject. Lots of different ideas, lots of different facets of it, many of which are tools, useful tools, not just inside of topology, but increasingly outside of topology as well. If you try to step back and look at all the different sub-areas in topology, some of which are listed on the screen, then a lot of them break up into different classes of techniques. You've got some techniques which are more descriptive. They take a space, or they take a mapping between spaces, and they give you some sort of description. And my computer is locking up. Why is it spinning? Okay, well, having a Microsoft moment. You have some branches of topology, or some tools in topology that are integrative, that allow you to take local bits of data and stitch them together. You've got some branches of topology that are more obstruction theoretic. They tell you whether a given problem is feasible, and that's usually some sort of algebraic computation. These are all things that are really important outside of topology. It's important to take a complicated system and have a concise way to describe its global features. It's important, very, very important, to be able to go from local information about a system or a space to global understanding of that system. That is an increasingly important problem in engineering and science. And the one that most people in engineering and science would not recognize as being as important a tool is the obstruction theoretic viewpoint. This is one of the things that topologists have really done right, is thinking of the world in terms of obstructions. Instead of, given a hard problem, just drilling down and trying to estimate. First, step back, say, what's the obstruction to solving the problem? What's the feasibility of the problem? And that usually winds up being some algebraic computation that you really can do. We've been working at topology for 100 years plus now, and we have some very, very deep tools, some of which the rest of the world have discovered on their own or have learned, but a lot of which we've kept to ourselves thanks to difficult notation and obscure literature. Okay, so let me stop with the propaganda, move on, just list some interesting applications that I've not talked about, some open ideas that I'm mulling over in my head, some things that I think I can do but haven't written down, and some things that I have no idea how to do, and I'm just going to toss out. Okay. One of the things we talked about in the first lecture was some of Carlson's work in persistent homology. Persistence is a growing field. Carlson and his collaborators have been doing a great amount of activity in that. Let me mention a few things that I didn't talk about, some more recent ideas, very, very interesting stuff. Remember the idea. You have some filtration of spaces, some sequence of inclusions, and you could talk about homology classes which persist over some interval. That relates to statistics and data sets in terms of giving you statistically significant topological features of a data set, given a simplicial approximation. Well, one interesting open direction, which turns out to be very difficult as well as very important, is what happens when you have more than one parameter? What happens when you have a data set and let's say you filter it by increasing the radius of balls that you use, but you also filter it in a different parameter using, say, density or codensity of your sampling set? There are other instances where you would have more than one parameter to deal with. Seems like a no-brainer. Well, you've just got a more complicated sort of filtration. Just start doing the same thing. Do the module classification that was done for the one-parameter family. Hire an algebraist if you have to turn the big cranks, and then go. Well, if you do that, the algebraist is going to come back and tell you, hang on a sec. These module classifications, when you have more than one parameter, involve classifications over polynomial rings with more than one variable. And that's not so easy. That's not so easy. It turns out to be a very difficult problem. Carlson and Zomrodian have made some progress in terms of a coarser invariant, something called a rank invariant. Has some connections to algebraic geometry. Really interesting problem that would have significant impacts in dealing with data if you could do multi-parameter persistence well and algorithmically. Here's a different idea. Instead of looking at multi-parameter diagrams, look at single-parameter diagrams. We're used to thinking about inclusions of spaces. That gives you a diagram that looks like this. You're always moving in one direction. What happens if you flip the direction of some arrows? If instead of inclusions, you have something more general. Something that might happen in the context of statistics would be a diagram like this, where you have, say, two subsamplings of your data set, and you look at the topology of this subsample and the topology of this subsample, and then you compare it to the topology of the union of those two subsamples. What does that correspond to? That corresponds to some consistency. If you take a subsample and you look at what the topology tells you about that, you look at another subsample of your data, you look at what the topology tells you about that, are they giving you the same topological features or not? Well, it's not just a function of, say, the Betti numbers, because you could be computing totally different holes. What you need to do is look at whether in the inclusion they're giving you the same generators for homology or not. And if you have a sequence of different subsamplings, that would give you a diagram like this. It turns out that one can work with any one-dimensional diagram, no matter which way the arrows are going. This is a recent bit of work by Carlson and De Silva that involves, in its analysis, quivers and other very interesting and relatively deep mathematical ideas. It turns out to be very, very relevant to consistency in statistics. Okay, lots of other open problems and interesting directions in persistence that I'm not going to cover. Let's move on. Let's talk about something else that's statistical, but something having to do with modes. You don't have to know any statistics to understand this, which is good because I don't really know any statistics. Let's talk about a distribution over space, and let's say it's bumpy. And let's say it's a continuous, reasonable distribution. Get rid of any of the little noise in there, smooth it out a bit. You have a bumpy distribution. Here's a question. How many bumps are there? How many modes are there? Well, you look at the picture, and that's there's three modes. You've got three humps, and they're added together. One thing that statisticians would be interested in doing, given a distribution like this, is to say how many modes there are. Let's say they use an additive interference model. So you have some modes, and you add them together to get this. Now, a statistician would be tempted to choose as a normal mode or a basis mode something nice, like a Gaussian. But there are other things that you might choose as well. A statistician or an analyst would be tempted to frame this in terms of an analysis problem or a calculus problem. If you've got Gaussians, right, how do I approximate this as a sum of Gaussians where I can, squeeze and stretch? And that gives you some simple analysis problems. How would a topologist deal with this? Well, I don't want to restrict to something that's Gaussian, because what's the formula for that? It's got that e to the minus, I don't know, I can't remember. That's why I went into topology. So, how do you do things where your modes are just things that go up and then go down? And that's it. there is an interesting problem associated with interference. If I have something like this that's got 3 humps in it, but with an additive interference, it might be that that central maximum is fake. It's caused by interference from 2 tails of the real modes that you have. Well, again, if you phrase this in terms of adding Gaussians together, then it becomes an analysis problem. If you do it topologically, however, if you say, what if we look at unimodal distributions, so things that just have one critical point, one maximum, no other critical points, they go down. Then you wind up defining the following thing. Given a distribution from your space to, let's say, the non-negative reals, what's the minimal number of unimodal summands that you can add together to express it, your original distribution, as that sum? Or again, by unimodal, I mean goes up, goes down, or if you like, all the superlevel sets are contractible or empty. We're calling this the unimodal category in deference to the Listenic-Schnirelmann category. Remember, LS category of a space is how many contractible patches do you need to cover that space? This is giving you something like a Listenic-Schnirelmann number, but instead of applying to a space, we're lifting it to data or distributions over a space. Now, why is this potentially useful? Well, the obvious lemma is that this unimodal category is invariant under coordinate changes. You can hit your domain with any homeomorphism you like, and it's not going to change what a unimodal distribution looks like. And we were motivated to do this work by the following context, where this distribution that you're getting is being sampled by some sensors in your domain, but the sensors don't actually know where they are, so you don't have any coordinates. So you can't really talk about Gaussians and things like that. You have to do something more topological, more coordinate-free. And this seems to be a good definition for trying to get a lower bound on how many modes your signal has to have. For example, if this were a frequency domain, and you had a number of people communicating and sending signals, and each signal smears out relative to some central frequency, then if you computed the unimodal category of the signal strengths over the frequency domain, then if you thought that there were only 2 people sending signals, but you're getting a unimodal category of 3, then that tells you that there's someone else definitely broadcasting something out there, and you might want to take a look at that. Of course, it's just a lower bound, just like LS category. Now, everything works great for a univariate distribution, for a distribution over a one-dimensional manifold. We have a nice, very, very straightforward algorithm that sweeps through the distribution, breaks it up into unimodal pieces, and that turns out to be the minimum. The minimum is realized, and it's very easy to compute. What turns out to be really difficult in this subject is what happens when you have a multivariate distribution. Even 2 dimensions, which seems pretty easy, turns out to be a little bit difficult, in part because of braiding phenomena, right? Your support for your unimodal distribution has to be some nice contractible patch. But of course, contractible sets in the plane can snake all around. I'm not so optimistic that it's going to be possible to get decent algorithms when you're looking at distributions, even over the plane. But I hold some hope that it might work. All right. Well, let's keep going. We're walking down the statistics road, and there's a lot of interesting connections between stats and topology. Let's talk about clustering. So clustering is an essential thing that one does with a data set. Even to someone who hasn't seen anything in statistics before, it's pretty clear what clustering ought to be and why it ought to be important. You have a data set, And let's say that you've got decent metric data in this context. So you know the distances between these points. You're in some Euclidean space. Then, how do you group your data set into clusters? How do you draw boxes around them and say, here's a group, and here's a group, and here's a group, in a way that's sensible? You might cluster it like this. You might cluster it in larger patches, depending on the phase of the moon and how you feel that day. Here's a very, very interesting theorem by John Kleinberg at Cornell having to do with clustering algorithms. What's a clustering algorithm? It's got to be a function, a machine, that when you input this data set with distances between it, it outputs clusters. It says this group, this group, this group, this group. So consider the following clustering algorithm. Has the following three properties. It's scale invariant. That means that if you just do one of these kinds of things, then it doesn't change the clusters that it gives you. That's sensible. That's a good property for a clustering algorithm to have. It's rich, which means that given any number of boxes, let's say n, there exists some data set that your clustering algorithm will break up into n different boxes. Again, that's a reasonable property to have. That's a non-degeneracy sort of property. And last and most importantly, your clustering algorithm should be consistent, which means that if I have a clustering algorithm that breaks this data set up into 4 boxes, if I change my data set so that within each cluster the points get closer together, or at least no farther apart, and between the boxes the points don't get any closer and maybe move farther apart, then what should the clustering algorithm give you? The same boxes, right? If I do something like this, it had better give me the same clusters, or at least not break up any of the clusters that we already have. Okay, so here's the theorem. No such algorithm exists. You can't have all 3 properties. You can have 2 of them, but you can't have 3. This is analogous to an arrow impossibility theorem or some of these topological social choice results. Okay. Well, that's an interesting result. It's a little bit depressing that something like that doesn't exist. Let's change perspective. Here's a wonderful idea by Carlson and Memeli. They're going to interpret a clustering algorithm as a functor between categories. What's the categories? Well, the input category is going to be the category of finite metric spaces. And the output category, oh, I should have said finite set instead of set, but you know what I mean. The output category is the category of finite sets. Those are your clusters. Now, for your input category, I have finite metric spaces. What are the morphisms? Well, for this theorem, this condition right here says that the morphisms you should look at are distance non-increasing maps. Right? And to have a functor between these categories, the functoriality really means that you're respecting this the distance non-increasing morphisms on the inputs. Okay, so, well, like everything else in category theory, this is just language, right? It's just an interpretation that this theorem says that there is no non-trivial functor from this category to this category. Okay. I confess, I'm doing this on camera, I confess, I used to denigrate category theory as being nothing more than, well, I won't say what I said back then, but I've changed my mind in recent years, and this bit of work is one good reason to change your mind if there's anyone in the listening audience who is a category theory skeptic. Why? When you translate it to this category theoretic framework, it tells you the right thing to do next. If you want a better result, if you want a result that's more positive than this negative result, what should you do? You should look for functors between an input category and an output category, but you might modify these. You might change them. You could change the input category, or you could change the output category. And it seems as though the study of such functors is completely open. No one's really thought about it until Carlson and Memely. And they will admit that they haven't gone very far down that road. Here's one thing that they have done, and I'd like to take credit for calling this cluster functors, although I might get in trouble for doing so. Okay, here's a more positive result. If you modify the output category, keep the input category the same, distance non-increasing morphisms on finite metric spaces, take the output category to be not finite sets, but finite persistent sets. So finite sets that are parametrized with one parameter. You'll see what I mean. Then there does exist a functor to this output category, and it is unique. There's a unique functor that does this subject to the following normalization condition. If you input 2 points, then the output persistent set is the following. You should think of horizontal slices as being your clusters, and then in the vertical direction you have your scale parameter. So at sufficiently small scales, your cluster functor gives you 2 clusters, and then at sufficiently large scales, your cluster functor groups these together into one box. That's a reasonable thing to do. That's something that statisticians have done before. They've talked about multi-scale clustering, but this is a new perspective, thinking about it as a functor and then showing uniqueness. I think this is a really lovely result that hasn't received enough attention and for which there's a lot of work left to be done. Okay, so when someone asks you, what's category theory good for, I would point to this as something that I could explain to someone who doesn't know anything about category theory as being something useful. Okay, let's keep going. We've talked over the past 2 days a bit here and there about sensor networks. One of the things that we didn't really discuss was coverage problems, where if you assume that each sensor node has some domain that it controls or it senses or it covers, then given a network, and just knowing what the communications network is, you'd like to get a decent approximation of what the coverage region is. That is clearly a topological problem. That's clearly the kind of problem that basic homology theory is going to knock off for you very, very easily. Vin De Silva and I wrote some papers on this. I'm not going to go through the details because I think this audience can very readily believe that some simple results having to do with the homology of the underlying communications network can give you criteria for when you have coverage or when you have a hole in coverage. And if you want to read more about this, you can see some of the articles that are floating out there. What I would like to point to is an open problem that Vin De Silva and I thought about solving, and we thought it would be easy, and we thought about it a little bit, and then we got frustrated and moved on to some other things. I still think it's very solvable. I still think it should be doable in an elegant manner. And this is the problem. Let's say that you have very, very dense coverage. You've got lots and lots of sensors, and they cover your domain really well. In fact, you've got so many sensors that you put a lot of them to sleep. This is something that you do in practice. Power is the quantity that is most scarce in sensor networks. So you don't want to have everyone on all the time. What you want is to have enough people on to give you coverage. Everyone else, you put them in sleep mode, where you can wake them up if you really have to, but you want them to be in a low-power sleep mode. Now, someone drops a fail bomb on your network, and one or more nodes goes out, giving you some holes in your coverage domain. Your goal is to wake up only the sleepers that are necessary to restore coverage. So in sleep mode, you've got a whole bunch of nodes that could take over and could cover your domain. There's no lack of nodes, but you want to figure out who you should wake up. If you wake everyone up and then build a new cover and then put everyone back to sleep, that gets the job done, but that's very wasteful. It's very wasteful. If you assume that the nodes that are awake have some knowledge of their sleeping neighbors, whom should they send wake-up signals to? I think that's a pretty concrete problem. I think it should have a solution that's elegant, that's very localized. You don't have to get the whole network to coordinate. It should be a local problem. It should have a nice homological formulation. But without coordinates, I think it gets a little tricky. I'm not sure. Okay, let's stop talking about sensor networks. Let's talk about something that I hope this audience will like a lot. Many of the talks that we've heard in this conference have been along the geometric group theory side. I can remember first learning about geometric groups from some graduate students that I was talking to. One was Kim Ruane, and she was explaining this stuff all to me when she was a graduate student and I was a graduate student. And I remember thinking, that's really nice, but I'm never going to have to know any of this stuff because it's not useful for anything. I've lived to regret those words after having published about a half a dozen papers using cat-zero geometry. A couple of them are on problems having to do with chasing bad guys or pursuit evasion problems. This is a classical set of problems in game theory where you have some domain and you have a pursuer and an evader. And the evader runs away, and the pursuer chases the evader. And the problem is, who wins? Does the good guy catch the bad guy, or does the bad guy run away? There are a million variations on this problem. You can have bounded domains. You can have unbounded domains. You can have equal speed. You can have constraints on how you move. I'm not going to be able to tell you much about this at all. Let me tell you, though, that almost all of the literature in game theory on pursuit and evasion uses partial differential equations to solve the problem. And that requires dealing with the boundary conditions. And that requires having boundaries that are nice, that are smooth, or even if they're polyhedral, you have to have a convex domain. Almost all the results in literature are either for two-dimensional simply connected domains or n-dimensional domains that have to be strictly convex. And when you hear that, the light should go off in your head that this is really a cat-zero phenomenon. So in joint work with Stephanie Alexander and Dick Bishop, we've been going back and looking at some of those old game theoretic results and then reproving them for arbitrary cat-zero domains, typically subsets of Euclidean space, finite dimensional. Things get a little trickier when you're in infinite dimensions, things like that. But there are a lot of interesting applications of cat-zero geometry, not just to these simple game theory problems, but to control theory in general. A lot of the techniques that the cat-zero world has developed are really going to be useful in not just game theory, but control theory. And I would very much like to see a bit more crossover and a bit more interaction. And if you know a lot of geometric group theory, a lot of bounded curvature techniques, I think you really have a skill that people outside of the geometric group theory world are going to be interested in. So keep that in mind. Okay, let's talk about coordinates. This is a very interesting bit of work that I don't think it's been published yet. I certainly don't think it's gotten the attention that it should. This is by De Silva and Morozov and Vedamo Johansson. And this has to do with, again, with data sets. Let's say that you have a spattering of points in a Euclidean space that gives you something circular. How do you set up coordinates to register that? You just want to write down an angle for these data points. If this was points in the plane, sampling some annulus, If things were nice and convex, you know what I mean by convex. There's the outer boundary, there's the inner boundary. It's a difference of convex sets. Then there are techniques that work. Very, very simple. But if you're in higher dimensional space and your circle that you have point sampled from is not convex, if it twists around, and in particular if it's embedded in an unusual manner, then all the standard algorithms that I and that they are aware of don't work for giving you an angle. So they, of course, take a topological approach. And the starting gate is the following. If you're looking at a function that gives you an angle, right, that's a map from your data set, or rather a simplicial approximation to your data set, to the circle, then, of course, we know how to classify such maps. That's just the first cohomology. Oh, need another cigarette. Excuse me. Okay, so if you want to get your hands on the first cohomology in integer coefficients, then that will be a good way to get an angular coordinate. The way that they do so is a kind of a twisty road. They wind up diffusing to real coefficients for simplicity in terms of computations, and then they have to do a little bit of Hodge theory to get that. Okay, there's some algorithms. It works. Great. End of story. What happens if instead of a circle, you have some higher dimensional non-trivial set that you want to come up with coordinates for? Let's say you have a two-sphere. You might think that you could just turn the crank and do the same thing. Unfortunately, your starting point, well, that's a little bit different, isn't it? So a lot of interesting open problems there having to do with setting up coordinates for data sets that are embedded in a high-dimensional space in an unusual manner. Okay. Are you tired yet? Because I have some more to go. Let's go back to the subject of yesterday's talk, which was integration with respect to Euler characteristic. And one of the things that I didn't talk about was a concrete application of this real-valued Euler integral. Remember, there were some nice connections with Morse theory. That was very good. What might that be useful for? Oh, for all kinds of things. Here's one example. Let's say that you have a hole in your integrand somewhere. You know what the integrand is on the plane minus some hole in the middle. And what you want to do is come up with a decent approximation for what the integral of the function over the entire plane is without knowing what's in that hole. Excuse me. So look at the following situation. Let's say that you have a nice round hole in the middle of your plane. And let's say that your integrand is 1 at the top and 1 at the bottom, and then 0 along the edge. And it does whatever outside. I'm just going to look at what happens on the boundary. Now, what might happen? Well, you don't know. It might be that there's one target here and one target here, in which case your reasonable answer should be 2 for the integral. Or it might be the case that there's one target that just goes through the hole, in which case the reasonable answer is 1. And you don't know which is which. Now, here's a heuristic. This is a hack. It seems to work. I'm not quite sure why. I think the right thing to do is to take the harmonic extension of this function over the hole. If you were to do that in this case, then you would wind up getting a saddle point at height c, where if everything's nice and symmetric, c would take on the value 1/2. What would the integral with respect to Euler characteristic be? Well, let's see. It's the sum of the maxima plus the sum of the minima minus the sums of the saddle heights. So in this case, it would give you 1 plus 1 minus c. If everything's symmetric, then c takes on a value of 1/2, and you get an expected value of 3/2 for your integral, which is exactly what you ought to have in this nice symmetric situation. Now, if you were to deform that hole and change the geometry, then it seems less likely that a target would wind its way through this deformed hole. And indeed, if you take a harmonic extension, then the height of this critical point would be much closer to 0 than to 1, which means that the expected value integrating this harmonic extension would be much closer to 2 than to 1. That seems to work. But in order for me to say, well, this is the expected value, I need to say with respect to what? How am I moving things around? This seems to touch on some ideas in geometric probability. I have a feeling that there's a nice theory that one could build here, but I'm not exactly sure how to do that. I think that's an interesting open problem that, again, should have some nice connections with Morse theory. Excuse me. Oh, it's no fun being sick. Okay. Again, since a lot of people in this group are very interested and very knowledgeable in geometric group theory and in spaces of bounded curvature, let me talk about a type of cubical complex that I've played around with for many years that I invented to help understand problems involving reconfiguration. This is related to the stuff we talked about before with moving robots around on a graph and doing so discretely by doing these local moves where you slide along an edge. There are a lot of generalizations of that lead to some interesting configuration spaces that, just as in the case of configuration spaces of points on a graph, always give you a cubical complex and always give you a locally cat-0 cubical complex as well. I'm not going to give you the theory. I'm just going to do one or two examples and then ask some questions. So here's a game. I've got tokens on a graph, just like before, and I have some local moves that I can do to rearrange the tokens, just like before, and I'm going to build a configuration space, a cube complex, based on that. Here's the deal. The states are labeled vertices of a graph. I'm going to draw a pentagon, in this case, with 5 different colored labels. And the moves, or I'm going to use suggestive language, the generators are, instead of sliding points along an edge to an unoccupied place, well, everything's occupied, we're going to flip 2 tokens along an edge. So do something like this. That's a generator, and that's a generator where I flip the 2 tokens, and I get different states. Sometimes I can do 2 generators in parallel at the same time. When I can do that, what does that correspond to in the Cayley complex, if you will? That's going to correspond to a square. So the vertices of this cube complex are going to be states. The edges are going to correspond to doing these generators, flipping, going from one state to another. And then if you have 2 generators that commute, that can be done independent of one another, then of course that gives you a box, a square in the Cayley graph of this system, in the transition graph, and you fill that in with the square. If you created a more complicated game with a graph and with local moves, transitions that you can do, local changes in state, then you could likewise build up some big cube complex. It would always be locally cat-0. In this case, everything is perfectly homogeneous, and a neighborhood of a state, of a vertex, looks like 5 squares put together. You do a little Euler characteristic computation, and you see that for this example, the state complex, or the cube complex that you get, turns out to be a closed orientable surface of genus 16. And you can interpret this algebraically in terms of the Cayley graph of the symmetric group S5, where you look at a presentation where the generators are certain transpositions, and filling that in by squares gives you this genus 16 surface. Okay, this is just a toy example, very, very simple. Here's another toy example of something that you could build. Let's say that your states are a length n planar chain in the planar lattice. And then my moves, or my generators, correspond to rotating the free end or flipping the corners, exchanging an interior for an exterior corner, something like that. So I can flip the corners, and some of them I can do in parallel, and some I can't. Now, if you, again, turn this into a cubical complex by filling in squares and cubes when you can do things independent of one another, then you wind up getting, well, some potentially interesting complex. It's not all that interesting. It's contractible. In fact, it's going to be contractible for any length. It's a little bit interesting when you start doing this for robots that are built out of modules where you can do local moves. But again, let's just think you've got some combinatorial game with local generators or local reconfigurations, and then you build some cubical complex as its configuration space. What do these state complexes look like? Well, there are a couple of results that we have that I think might appeal to this audience. So if you take any state complex for any reconfigurable system with a list of generators, then the fundamental group of that cube complex, of that configuration space, embeds into a particular right-angled Artin group, the one given by the local moves, the generators, where you commute algebraically if and only if your moves commute physically. And that's kind of nice because we can build lots and lots of manifolds as these configuration spaces, as these cube complexes. And that tells you that there are lots and lots of hyperbolic manifold groups that embed in Artin right-angled groups. Again, I think that's a known result, but it's kind of fun that we can get that explicitly just by building some simple games and playing around with things like that. There's a lot of open problems, especially concerning which fundamental groups you can get as these state complexes. These are very closely related to some of the cubical complexes that Donnie Wise and his collaborators have been working with, the so-called special cube complexes. These are slightly different, but very closely related. Okay, well, let's change gears. Let's talk about lightning, because lightning is awesome. We might see some lightning today. We saw some lightning yesterday. Did you guys see that? Did you guys get hail? I got hail north of town. Oh, my gosh. I thought my rental car was going to be destroyed. Okay, let's talk about lightning. I hope I don't have to deal with that as well. Okay, so what happens when lightning strikes? When lightning hits the Earth, bam, and it sets off a wave. It sets off a wave in the ionosphere that travels. And, oh, there we go, the graphic. Good, lightning. And you can detect that wave if you have a radio, if you have very, very simple devices. You can hear that wave at very, very low frequencies. In fact, most devices that you have attenuate out the low frequencies, in part to get rid of the noise that comes from lightning strikes that might be nearby. Now, how far do these waves propagate? They go over most of the surface of the Earth. They go over most of the surface of the Earth. They propagate a long way. And you can hear them with very, very cheap, inexpensive devices. Now, around the planet, there are weather stations that figure out, that record exactly where and when lightning strikes happen around the world. If you have access to that data, and if you're walking around with a device that just records the time whenever a wave passes overhead, then you can go back, correlate with that data, and figure out exactly where you were just based on lightning strikes about every 30 milliseconds or so. So, you know, I'm doing this in slow motion. Very slow motion. Wouldn't it be cool if you could build a GPS system that's based on lightning rather than based on communicating with satellites? Why might you want to do that? Well, you probably don't. GPS works great. It's going to be very accurate. But, you know, if the sun ever decides to act up and wipe out all of our satellites, then GPS is going to go down. GPS doesn't work when you're underground, doesn't work when you're underwater. These ionospheric waves can propagate through materials a little bit. Might be cool to have a GPS system that's built on lightning, just to be able to say, I did this with lightning. I don't know. More generally, the air around you is full of waves, digital TV waves, radio waves, microwaves, new waves, I don't know, all kinds of waves are bouncing all over the place. Can you take advantage of these ambient waves that are just running around to figure out where you are, to figure out how many buildings are in your neighborhood? Yes?
Did you compensate independently of Batman?
Oh, is that, I didn't see that movie. Is that in there? Cool. Using cell phone signals. This is not an original idea to me. This is, there's a small literature on this called Signals of Opportunity. And the idea is to take advantage of signals that are just floating around to solve problems. Oh, it was in Dark Knight. Oh, man. Well, I guess I'm already obsolete, because if Batman knows about it, then everybody knows about it. Yeah, superhero movies are a really good way to find out what DARPA is up to at any given point in. Oh, that's on video, isn't it? Okay, well, I'm fired. That's the way it goes. Okay, so lots of interesting problems associated with this. These are not so obviously connected to interesting topology, but I really think it is. So, for example, if you just have some transmitters bouncing around, and you want to know if I'm a receiver standing somewhere, do I get a unique channel response, a unique signal response, if I just record the time when the signals come to me? If I read off a sequence of 7 times that signals hit me, is that going to be unique? Or if I move to a different part of the room, might I get the same sequence or not? Michael Robinson and I have played around with that problem, and it turns out to have a very simple solution that involves the Whitney embedding theorem, as you might expect, and some of those bounds for embeddings of manifolds wind up being very relevant here, and they give you sharp bounds for how many transmissions you need. And again, in cases where we've explained this to people in applications, their first response was, you're wrong or you're lying, because we don't believe that you could get by with that little information. Okay, let's wrap things up with some more out there remarks having to do with combinatorial optimization problems. Now, I don't know how many people know much about combinatorial optimization. I didn't know that much until fairly recently. But it's pretty big literature. It's got some very fundamental ideas. One of the main results that a lot of people care about in combinatorial optimization is Helly's theorem. This usually gets explained in convex geometry contexts, and most people think that it's a theorem about convex sets. How many people have seen Helly's theorem before? Yeah, this is a really important one. It says if you have a collection of convex sets in a d-dimensional space, n-dimensional space, and if each n plus 1 tuple of them has a non-empty intersection, then the full set has a non-empty intersection. That doesn't seem like a very applied result. It winds up being very, very useful in some optimization problems. And the right proof of this is the topological proof. As Helly knew, as lots of people have known, but you don't always see this in the literature. So for the benefits of the video audience who doesn't know this so well, let me just flash up the idea. The right way to do this is in terms of check homology, right? If you look at the nerve of the cover, then, working inductively, let's just say you have n plus 2 sets. Then by the assumption, the nerve of the cover is either a full simplex dimension n plus 1, or it's the boundary, which is, of course, an n sphere. Now, the nerve lemma tells you, because this is a good cover, being convex sets, all the intersections are contractible, that the union is homotopy equivalent to the nerve. If you didn't have a common intersection and the nerve was really the boundary of this n+1 simplex, then you would have a subset of Rn that was homotopic to an n-dimensional sphere. No can do. Voila, go by induction. Now, why is this the right approach to Helly's theorem? Because it tells you how you can change the assumptions. You don't have to have convex sets at all. What you really have to have is a good cover. And if you want to do more generalizations, then this points the way as to how to do that. That's a canonical example for me why an algebraic topological approach is going to be useful in a lot of combinatorial optimization problems. There's another class of problems, much more modern, that not so many people in mathematics know about. It's very important. This has to do with network coding. So you like using the internet. You've got packets moving around on the internet. How does this work? Let's say that you have two packets that you want to send from a source to two different targets. Let's call those packets A and B. Well, if you want to send it over this network, then one way to do it is, let's say that you send A here and B here. The sensible thing to do is to take turns. You let B go first and propagate its information to both senders. And then you, once the coast is clear, then A can propagate its information through the network to both receivers. And then they each get a copy of A and a copy of B. That's great, but it takes time. If you allow your nodes to do a little bit of coding, some linear algebra, these packets are typically going to be elements in a vector space over a finite field. Let's say that your nodes can do basic linear algebra. Then one thing you could do is, if you have A here and B here, then at this node, you could combine them. You could add the signals together. You get A plus B. And then you propagate A here, B here, and A plus B down both sides. And then at the end, each sender gets a copy of A and A plus B, and B and A plus B, from which it can extract both signals, again, doing linear algebra. What's nice about this, it happens in less time. You don't have to wait to take turns. So the small but very exciting literature on network coding tries to figure out things like network capacities if you allow linear algebraic operations. Most of the proofs in this business are, linear algebra and induction, and you bang on it with a hammer. I think that there's a lot more that one could do with some sophisticated ideas. And my sophisticated idea of choice is, like yesterday, some notions of sheath theory. So let me say what I mean by a sheaf and why I think sheaves, and a particular type of sheaf, are going to be relevant to applications. Again, in the simple setting, a sheaf is going to be a functor, contravariant functor, from open sets of a space to something algebraic, let's say category of vector spaces over some field. Might do something more general, but let's keep it simple for now. Let's say that you had a robot that's running through a system of hallways. And the robot has a omnidirectional laser on top of its head, and it keeps track of what it can see. If it's in the middle of a hallway, then it's got two directions that it can see, forwards and backwards. It builds a two-dimensional vector space of observations. And as it moves from point to point, right, it has a two-dimensional vector space at every point, and it has a consistent notion of what's forwards and what's backwards. And that's the case until it gets to a branch point in the hallway. And then all of a sudden, there's a third direction. There's a third dimension that opens up. And the fiber, the stalk over that point, the data is not the same. It's a vector space of different dimension. But it knows how to correlate the forward and the backward direction with respect to this new basis element that's opened up. Right? This is a very, very simple example of a sheaf, but I think it's a very, very good way to explain what a sheaf is to someone who is not a mathematician. You want to carry data along at every point, but the data is allowed to change dramatically as you move around from point to point, but you could still make a consistent sense of what happens as you move around. Now, this is a very simple type of sheaf, something like a cellular sheaf, a particular type of stratified sheaf. But something like this is going to be useful in the context of network coding. So let's say that you have a network with a source and one or more targets. Excuse me. Let's say that each of these edges has some capacity, some integer non-negative capacity, how much signal it can carry. Then you can build a sheaf over this network as follows. So the stalk, well, let me say it this way. If I take an open neighborhood of an edge, a point inside the edge, then you get a vector space whose dimension is the capacity of that edge. It's how much signal comes in. If I take a node, then what's the value of the pre-sheaf over this node? Again, it's a vector space of dimension equal to all the incoming edges. Take the sums of the capacities of the incoming edges. It's how much signal flows into the node. That's what the dimension of the stalk over this point is. For a sheaf, you have to have restriction maps. If I restrict to a neighborhood of some incoming edge, then that's just a projection map. If I restrict to an outgoing edge, then that's going to be what? Well, the node does some linear algebra based on the incoming signals. So I can encode that output signal, take a projection map, that's going to give me the restriction. So I can encode all the coding that happens at the nodes into the pre-sheaf, turn it into a sheaf. And now, taking the étal space, you've got a topological space that has built into it all of the linear algebraic coding that your network does. Now, there's a bunch of papers out there on sheaves applied to all kinds of things. I haven't been able to make much sense of them. That's because it goes pretty hard into the category theory. I think the right way to make sheaf theory useful in these contexts is to pass to cohomology, is to use an obstruction theoretic point of view. So one result that we have with Yasu Hiraoka and Michael Robinson is to relate the classical min-cut max flow theorem in combinatorial optimization to the sheaf cohomology of these types of network coding sheaves. And I'm running out of time, so I'm not going to be able to talk very much about that. But we believe that there's some really good tools from sheaf theory that are going to recover some classical results and then be able to extend those to some new contexts, especially concerning network coding. All right, you've been very patient. You've listened to my ramblings for 3 days now. So let's wrap it up. But I have to do a little bit more propaganda. So if you look back at the history of mathematics, it's full of all kinds of abstract nonsense that we mathematicians have been pushing on the rest of the world and that they've complained about until they found out that they needed it, and then they adopted it, and they wound up getting better at it than we are in some cases, like, matrix algebra. Physicists used to complain bitterly about matrix algebra. Abstract nonsense. Why do you need that? We already know how to solve equations. And now they and everyone else on the planet has found out that it's useful. I believe that algebraic topology is very much in line with some of these other ideas that started off being obtuse, being seemingly too abstract to be useful, winds up being essential. And I think one of the things that's going to be really important is how we teach algebraic topology to others. I am very much of the opinion that 20 years from now, we're going to be teaching our undergraduate engineers basic homological algebra, not the hard stuff, basic homological algebra in a very good linear algebra course, because they're going to need to know basics of homology. That means that we need to practice explaining these ideas to a broader audience so that they will take off and take on a new life. And now I really am going to stop and thank you for your patience.